Pluto made them come all alongside. Pluto's circle crosses that of a few other planets. Pluto, the hard little planet on the outer scopes of our nearby planetary organization, is stirring up excitement on Earth. Ongoing reviews suggest a possible issue with Neptune, raising concerns among researchers and space enthusiasts. Key figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the ramifications of this cosmic event. But how did Pluto end up on a potential collision course with its neighboring planet? And what could this celestial conflict mean for life on Earth? Join us as we unravel how something massive may have collided with Neptune and how researchers are grappling with this significant anomaly. Pluto's unique orbit and its fascination. Once hailed as a planet, Pluto underwent a change in status when it was reclassified as a dwarf planet due to its unconventional orbit. Despite this downgrade, Pluto continues to captivate scientists and enthusiasts alike. Recent forecasts from esteemed researchers like Neil deGrasse Tyson and Michio Kaku suggest that Pluto's trajectory may intersect with Neptune's, raising concerns about potential consequences. The possibility of interactions between these two celestial bodies has far-reaching implications for Earth and our understanding of planetary dynamics. Pluto's journey around the Sun stands out due to its distinctive characteristics within our solar system. Its orbit is highly elongated, stretching across vast astronomical distances. Since its discovery in 1930, Pluto has yet to complete a full orbit around the Sun. Adding to its uniqueness, Pluto's orbit is highly inclined, tilted at about 17 degrees relative to the ecliptic plane. This means its path is more steeply angled compared to the orbits of major planets. One notable feature of Pluto's movement is its occasional intersection with Neptune's orbit. For approximately 20 years during each orbital cycle, Pluto moves closer to the Sun than Neptune, defying expectations based on their relative positions. The complexity of Pluto's orbit. Digging deeper into Pluto's orbital mechanics, we find that its path is not a perfect circle, but rather an elongated ellipse. This results in significant variations in its distance from the Sun. At its closest approach, perihelion, Pluto comes within about 30 astronomical units, AU, of the Sun. At its farthest, aphelion, it extends beyond 49 Australian dollars farther than Neptune's average distance from the Sun. Moreover, Pluto's orbit is tilted relative to the major planets. This inclination not only adds complexity but also influences its interactions with celestial bodies, particularly Neptune. When Pluto and Neptune cross paths, their gravitational forces subtly adjust their trajectories over time. This intricate gravitational dance highlights the dynamic nature of our solar system. Even though Pluto was once thought of as an isolated wanderer in the Kuiper Belt, its interactions with Neptune demonstrate the interconnectedness of celestial bodies, each exerting gravitational forces that influence the movement of others. Why hasn't Pluto collided with Neptune? One of the great mysteries of planetary science is why Pluto and Neptune have never collided despite their intersecting orbits. The answer lies in gravitational influences and orbital mechanics. Astronomers quickly noticed Pluto's unusual orbit after its discovery. Unlike most planets which remain close to the ecliptic plane, Pluto's tilted and elliptical orbit stood out. Despite their paths crossing, Pluto and Neptune remain in a stable orbital resonance, an arrangement where their movements are synchronized in a way that prevents collisions. This resonance ensures that Pluto and Neptune never come too close. Even when Pluto is at the part of its orbit that overlaps Neptune's, it is always at least 90 degrees away in its orbital phase. This effect, known as libration, keeps Pluto safely clear of Neptune's gravitational pull. Additionally, the VSOP variations, named after researchers who studied planetary motion, help explain why Pluto's eccentric orbit remains stable over long periods. While space may seem chaotic, these hidden patterns and gravitational rules maintain stability in planetary orbits. Pluto's orbit and future research. Despite the stability of Pluto's orbit, astronomers continue to study it carefully. The solar system is constantly evolving, and small gravitational perturbations over millions of years could alter Pluto's trajectory. Computer simulations have helped researchers understand how Pluto interacts with other celestial objects like Neptune. By tweaking variables in these simulations, scientists can predict possible future changes in Pluto's orbit. In the late 1990s, these studies revealed that Pluto's orbit has remained remarkably stable over billions of years despite its unusual characteristics. While the likelihood of Pluto colliding with Neptune remains extremely low, continued monitoring and simulations are necessary to track any unexpected changes. Understanding the forces governing Pluto's path helps scientists refine their models of planetary motion and solar system evolution. The broader implications of Pluto's orbit. Pluto's unusual orbit raises broader questions about celestial mechanics and planetary stability. In other star systems, similar gravitational interactions could lead to planetary collisions over long timescales. For example, in the TRAPPIST-1 system, where 7 Earth-sized planets orbit a single star, gravitational forces create orbital resonances. Over time, these interactions could destabilize planetary orbits, potentially leading to collisions. Researchers closely observe such systems to understand how planets influence each other's movement. The views of Neil deGrasse Tyson, Michio Kaku. Prominent scientists like Neil deGrasse Tyson and Michio Kaku have weighed in on Pluto's orbit and its potential implications. Tyson, who played a key role in Pluto's reclassification as a dwarf planet, argues that studying Pluto's erratic orbit helps us better understand celestial mechanics. He believes that Pluto's unique trajectory highlights gaps in our understanding of space and planetary dynamics. Michio Kaku, a theoretical physicist known for his work in string theory, sees Pluto's orbit as a valuable case study for space exploration. He suggests that understanding gravitational interactions like those between Pluto and Neptune can improve navigation for future space missions. Kaku also notes that studying anomalies in planetary motion could help scientists test theories about gravity, spacetime, and fundamental physics. Could Pluto and Neptune ever collide? While highly unlikely, a collision between Pluto and Neptune would be a significant event in planetary science. Such an impact could release vast amounts of energy, potentially shattering Pluto into fragments and altering Neptune's trajectory. The resulting debris could scatter through the solar system, affecting other celestial bodies. From a scientific perspective, such an event could provide valuable data on planetary collisions, gravitational interactions, and the physics of extreme conditions. It could even help test aspects of string theory by offering insights into how fundamental forces behave under intense gravitational stress. The continuing study of Pluto's orbit. Pluto's orbit, influenced by gravitational forces from Neptune and other celestial bodies, remains a subject of great interest. Despite its small size and distance from the Sun, Pluto's interactions with the rest of the solar system reveal complex and dynamic relationships between planets. The three-body problem, how gravitational forces between multiple celestial bodies influence each other, remains an ongoing challenge in astrophysics. While Pluto and Neptune are not expected to collide, studying their orbital dynamics provides valuable insights into planetary motion, space stability, and the fundamental laws of the universe. As research continues, astronomers will keep tracking Pluto's orbit, refining their models, and seeking to understand the intricate dance of celestial bodies that shapes our solar system. Despite Pluto's eccentric and inclined orbit, it has remained stable over billions of years. This stability is largely due to a special orbital resonance with Neptune. Specifically, Pluto is in a 3-2 resonance with Neptune, meaning that for every 3 orbits Pluto completes around the Sun, Neptune completes exactly 2. This gravitational relationship ensures that Pluto and Neptune never collide, as their orbits are synchronized in such a way that they always avoid close encounters. However, while this resonance protects Pluto from colliding with Neptune, other forces in the solar system could potentially alter its trajectory over extremely long timescales. The gravitational influence of other giant planets like Jupiter and Saturn subtly perturbs Pluto's orbit. Although these changes are minor, simulations suggest that over hundreds of millions or even billions of years such perturbations could accumulate, leading to unpredictable shifts in Pluto's path. Additionally, the Yarkovsky effect, a force caused by the way a celestial body absorbs and re-emits solar radiation, could gradually affect Pluto's trajectory. Though this effect is more significant for small asteroids, it may still contribute to minor alterations in Pluto's long-term motion. Could Pluto ever become a threat to Earth? Some theories suggest that distant celestial objects, including Pluto and even some Kuiper belt objects, could be influenced by external forces such as passing stars or galactic tidal effects. While highly unlikely, such perturbations could in theory destabilize Pluto's orbit and push it closer to the inner solar system. If this were to happen, Pluto could either be ejected from the solar system entirely or enter an unstable orbit that could potentially bring it closer to planets like Earth. Current simulations show no immediate danger of Pluto colliding with Earth or any other major planet, but long-term gravitational interactions remain an active area of study. Theoretical physics and the broader cosmic perspective. Pluto's unusual orbit provides a natural laboratory for studying the three-body problem, an area of physics that explores how 3 celestial objects interact gravitationally. This problem is notoriously difficult to solve because small changes in initial conditions can lead to vastly different outcomes, a hallmark of chaotic systems. Physicists like Michio Kaku and Neil deGrasse Tyson emphasize that understanding Pluto's orbit isn't just about tracking its position, it's also about refining our models of celestial mechanics, orbital stability, and even deeper aspects of physics such as string theory and quantum gravity. In particular, if Pluto were ever to experience a major perturbation or collision, it could generate significant gravitational waves ripples in spacetime that could help physicists test fundamental theories about the nature of the universe. Such an event could offer insights into